sampling. Okay. Now, this is actually a full chapter in your book. It's chapter 5. But we are gonna take only few concepts. So few main concepts. We are not gonna go through every single thing. There are lots of information in the chapter. So it's a good idea to make sure you capture the concepts that we will talk about today. And these are the ones that you are required to be familiar with, and even solving problems is gonna be within those concepts. Okay? So number one, we will talk about what is sampling, right? We will describe how to do the operation. Of sampling, so how to do sampling. Okay. We'll describe something called the sampling theorem. Okay. And this mainly discusses conditions for, and I quote this word because it's kind of a wide meaning word, but we will understand in a few minutes, or maybe like few tens of minutes. What do I mean by that? So the conditions for proper sampling. Okay, and proper here is just a wide word, and then I will give more details. What do I mean by proper later on? And then we will discuss the sampling operation. So what is sampling and how to do it? And then we will discuss the inverse operation, so the other way around, and that's called reconstruction. Okay, this is simply the inverse of the sampling operation. So once we know what is sampling, we will immediately understand what's meant by inversing that. Sampling is not a mathematical transform like the Fourier transform or Fourier series. It's an actual physical operation that you perform to get something out of it. Okay, so these are more or less the topics that we will cover from that part. If you go to the book chapter, you will find really, I mean, it covers those definitely, but it covers much more than that. Okay, so but as far as we are concerned with this course, this is what you need. You will get more details and more descriptions and more mathematical representations and more information about sampling when you go to your DSP, your digital signal processing. That's for computer engineers, and for electrical engineers, you go for the signals and filtering course, which is again a digital signal processing topic. Okay. So let's start. What is sampling and how to do it? So what is sampling? And simply, the answer to this is it is the operation of converting a continuous time signal into a discrete time signal. Okay, so if I want to represent this by a functional block diagram, so I have here something called the sampler block, okay, which is doing the sampling operation. Okay, and the input to this is going to be some signal x of t, which is simply just some continuous time signal, okay, as a function of t. The output coming out of here is going to be, we call it xs, okay, and it's going to be, again, a function of time, but since it's discretized, it's going to occur at certain instants of time, and we also can call it x of n ts, or when you go to the discrete description fully, it becomes x of n. Okay. Now what's TS? TS is the duration between one sample and the next. And it's always a fixed duration, which means that we are doing, or what we study in this course is something called uniform sampling, okay? So how would that signal look like? It's a discrete signal, as we said, versus time or versus n, whatever you like, okay? It's going to be, if we just imagine that this was the envelope of the original signal that we had over there, right? I'm trying to replicate. It's not that much a replication, but anyways. So this is gonna be just a value here, a value here, a value here. And typically we represent those values with something called the stem diagram. It doesn't mean that there is an actual line. There's just one value, but we draw it as a line to show the amplitude of that, okay? So this is a discretized signal, right? And it exists at 0, and then TS, and then 2TS, 3TS, and so on. The distance between one sample and the other is TS, which is called sampling time. Okay? And the fact that they are all equally spaced is, we call this operation uniform sampling. In this course, we will not study the non-uniform case. It's a more complicated case, both from an implementation point of view and from a mathematical representation point of view. But in some situations, it's necessary. Okay? But here, in this course, we focus only on uniform sampling. So the distance between one sample and the other never changes. It's the same between all the samples. Okay? Keep an eye on the terminologies. So x of t, the continuous time signal, xs of t, the discrete time signal, or without saying xs, we say x, but now nts. So it exists only at integer values of n of ts. It doesn't exist at all time. Or if we want to put it in the final discrete format, we just say x of n, and we understand that n goes 1, 2, 3, 4, 5. And between each one of those and the next one, it's TS. So we know that this 1 corresponds to TS, 2 corresponds to 2TS, 3 corresponds to 3TS, and so on. Okay? So these are 3 different ways to represent exactly the same thing, which is the sampled signal or the discretized, we call it the discretized or the sampled signal. Okay? That is the operation itself. How do we perform this operation? What kind of mathematics or actual implementation that allows us to represent this operation? So that's going to be the next part. So how to perform sampling. Okay. The simplest and the most straightforward way to do this is to remember that we had something called delta function. Remember the delta function? Okay, delta of t and its shifted version at any location t naught, delta of t minus t naught, right? And remember a nice property that we talked about this delta function is that if I have a continuous time signal x of t, okay, so this is my x of t, and I multiply this signal, so this is a multiplication operation, with a shifted delta at certain location t naught, so this is at t naught, this is delta of t minus t naught. If I multiply those two, the result coming out from this multiplication is going to be x at location t naught multiplied still by the delta of t minus t naught. So it's going to be simply a delta function, right? At the location where the delta was, so at t naught, but it's going to be scaled, that delta function is going to be scaled by the value of x of t at the location of the delta, t naught, right? Okay, so that property we discussed it a long time ago. Now we are going to capitalize on this property. Imagine that I have a continuous time signal. So now I have x of t. And instead of multiplying it with a single delta, I will now multiply this with a train of deltas. So I will do the multiplication operation, but this time it's with deltas that happens at 0, ts, 2ts, 3ts, minus ts, minus 2ts. They are all deltas with magnitude equal to 1. So we call this a train of delta. And we call this the sampling function. We typically give it the expression xp of t, the function that we use to sample continuous time signals. This is a function of time. Okay? So the result of multiplying x of t with xp of t, that result is what we will call xs of t, the sampled version of the signal t. Okay? Why this is the case? Look at what will happen when you multiply the deltas with the continuous time. What will happen? What's going to be the result?
Discrete values of this function.
Exactly. You picked the values of the function only at the locations of the delta, and you scaled the delta with those values. So this is a very proper or very nice, not proper, because proper, I used it for something. This is a very good representation of a sampled version of the signal. So the result of this multiplication, which is called x of s, is going to look like this. As a function of time, this is the sampled signal, xs of t. And if I imagine that this is the original envelope of that signal, the continuous version that we had up there, right?
What's x of p?
Sorry?
What's x of p?
It's called sampling function, a function that we use for sampling. Just wait. Wait, just naming. This is naming.
X of s.
Hmm?
X of s.
Sampled function.
So x of p to sample.
Yes, sampling is different from sampled. Okay, so one of them is the output of the sampling. That's the result of the sampling. The other one is the function that performs the sampling itself on the continuous time signal. Okay, so the result of this multiplication is going to be a delta with this magnitude here, and then another delta with this magnitude here, and a third delta with this magnitude, fourth delta with this magnitude, and so on. Right? So it's actually performing sampling of that signal, right? Each one of those deltas now is scaled by tracing the value of the continuous time signal at the location of the delta. So it's scaled by the value of the continuous time. So as if you took samples only from the continuous time, and you end up with a discretized version of the original signal, or a sampled version of the original signal. Okay? Again, just for naming, this is sampling function. This is the sampled signal. Okay, and this is the continuous time signal. So the sampled is basically the discrete time signal. It's the same now as our discrete time signal. Okay. Okay. I hope you are convinced with this in terms of just qualitative representation. Now, if you want to write, this is a general signal, it can be anything. How do I write this x of p as an expression? It's summation of shifted deltas, right? I have delta shifted at different locations, and I'm adding them together, so I end up with what we call the train of delta. Okay? So I can write xp of t as the summation from n equals minus infinity to infinity, a delta function of t shifted at location ts multiplied by n. Right? So if I put n equals 0 in this expression, I have the delta at 0. If I put n equals 1, I have the delta at ts. If I I put n equals 2, I have a delta at 2ts, 3ts, 4ts, minus ts, minus 2ts, minus 3ts, and so on. So I have all these deltas. When I add them together, since they are shifted from one another, they end up looking like that train of delta that I have over there. Okay? So hopefully you are convinced that this is a correct expression of this, of this train of deltas. Okay? Any questions so far? Okay. Now, let's perform this multiplication operation to see how the output function would look like. The sampled function, how it would look like. So this is x of p. Now, what we can do is plug this into the expression that we have here. So we plug it with this expression. So we end up with x of t multiplied by that summation from n equals minus infinity to infinity, delta of t minus n ts, right? And this is going to be equal to, if I multiply x of t, I can take that x of t, since this summation is over a variable called n, the x of t is constant with respect to that variable, right? So I can put it inside the summation, right? If I put x of t inside the summation, I have what? X of t multiplied by a delta at some location called nts. We said that when you have this x of t multiplied by a shifted delta, you can represent this as x at the location of the delta multiplied by the delta functions, right? So I'm gonna write this in two steps. So that's summation from n equals minus infinity to infinity, x of t multiplied by delta at t minus nts. Now when I look at this, this is a continuous time signal multiplied by a delta at this location. So I can write this as, from what we did here, right? I can write this as, so that's equal to, again the summation, nothing changes about the summation.
This is x of s, right? Calculating x of s.
Yes. Okay. So the summation stays as is. Okay. Why the infinity looks bad here? Okay. To infinity, and then I have x at the location of the delta becomes x at nts, right? X at the location nts multiplied still by the delta. The delta does not disappear in this case. T minus nts. Okay? And this is what we call this, what we have here is the final expression of the sampled signal. So this is basically this guy. This is xs of t. Okay? Simply the samples of x at locations nts multiplied by delta functions, which if you graph this, you get exactly what we have here, right? The samples of these are the values, right? Multiplied by delta functions. Okay? So this is the expression for the sampled signal. Okay, good so far. Now up to this point, we know how to perform sampling operation. How can I take samples from a continuous time signal to produce some discrete time signal? And we have also the mathematical expressions for everything. The original signal itself, of course, can be anything. And then the continuous time. And then the sampling function, it's written as a train of deltas. Those train of deltas are multiplied by the continuous time to produce eventually a discrete time signal that is still a train of deltas, but instead of all of them having the same magnitude now, they are picking the samples of x of t at the locations of the delta. So they have sampled that function. Okay, excellent. The question comes, how to pick ts? And that is the part where we ask the question, what are the conditions to perform proper sampling? Okay, so how to pick the value of ts? The value of the sampling time. I can actually make those guys close to each other or far from each other, right? Now what prevents me from making them very close to each other is the fact that this means that I'm going back to the problem of continuous time signals, that I have too many values, right? Problem of any continuous time signal is between any 2 points, you have infinite number of values. It's a continuous line, so it can be broken into infinite number of points, right? So if I make those samples very close to each other, I end up with huge amount of data that's going to be prohibitive in terms of dealing with it on a computer. The target of doing sampling is to convert things into smaller amount of values that can be processed on a computer, for example. Okay? So from one point, I want TS to be as large as possible, because this would mean that I will have to deal with smaller amount of data, right? So let's start this argument in the next slide. So what are the conditions? For proper sampling. Okay? So number one, when you are trying to answer this question, the first thing that faces you is I would like to have as little number of samples as possible, okay, to reduce amount of data, okay. That's a storage issue, right? So in this case, I want TS to go large. I want to increase TS. Okay, nice. Well, what if I increase TS and I end up with the whole signal, I take one sample? Where is the problem? Just for the whole duration of the signal, I take only one sample. Now imagine that I had a signal that looks like the wave that I drew previously, and I have another signal which is just a straight line. And I pick one location and I take a sample and that's it. And I give it to the computer. Now I want to process and get the original signal, right? After processing. How would I know if the original signal was the line or the curve that I drew or whatever, right? So that would tell me, I mean, intuitively, the more samples I take, right, the better I will be able to recover the original signal, right? So now from the other side, in order to reduce or actually even eliminate, okay, loss of information. Okay, because when I take samples, I don't take all the values of the signal, so I'm losing some information, right? Is it true? Am I losing some information or not? The reality that we will discover is that there is a particular threshold beyond which, if you do not achieve that threshold, then you will lose information. If you do respect that threshold, then you can recover your original signal without any losses. That's what's called the sampling theory, okay? And we will see first why this is the case, and after that we will just state the theorem, okay? So anyways, in order to reduce or even eliminate the loss of information, I would like to increase the number of samples. Now to increase the number of samples, this means basically TS should go actually smaller, not larger, right? So that's the opposite. So there must be some balance point or some condition where TS is not too large, but it's not too small, okay? So we'll see how to figure out this, okay? Now let's look at, in order to understand, and that's another very good sampling theorem that we'll discuss now, where it came from. That's another very good example why we need the frequency domain, because there are some aspects that we only understand when we look at frequency domain representation of a signal. We will not be able to figure it out by just looking at the time domain representation, okay? Okay, so to answer this, to answer the question, okay, let us visit the frequency domain representation of the sampling operation. Okay, so let's do that in the next. So sampling using the frequency domain glasses. So we are looking at things from or the frequency domain perspective. So we are looking at the same operation, but now we will convert everything to frequency to see what's happening in the frequency domain. Okay? Let's start by our generalized signal x of t. So we have a signal x of t, right, which is the continuous time signal. And that's too long. And again, it just can be anything, okay? And that signal x of t, yes? Yeah, just glasses. So we are wearing the glasses of the frequency domain. That's what I meant. So this means perspective, okay? So I mean that we are not really changing the operation. It's the same operation, but rather than looking at it in front of us from a time domain perspective, we will convert everything in frequency domain and see what happens in the frequency for the same operation. Same signal, same operation, okay? So if this is x of t, we will assume that it has some frequency domain representation. Let's say, for example, that frequency domain representation looks like this. Okay, just some general, as I assumed here, some general signal. By luck, when I converted it using the Fourier transform, I found it to look like this. Okay, the only condition in order to be able to perform sampling is that I have to deal with signals that have a finite bandwidth. So I cannot really deal with signals that spans frequency up to infinity. And practically speaking, that's impossible. And practically speaking, if my signal has a very wide bandwidth, similar to what you did in your project, I will come at some point and cut and say this is my end. I'm not going to consider the remaining parts of the frequency domain. Okay? So in all cases, I have to deal with some finite bandwidth signal. So a signal with finite bandwidth, let's call that bandwidth B. So that's the bandwidth of your original signal, and let's call it B. Okay? Again, these are just general. It can be anything. It can look any shape, but important is it has some end for its frequency, or I define an end for its frequency, okay? So this is your x of omega. When I converted this general x of t, I found that its frequency domain looks like what I have here. Okay, nice. That's the first thing. What other things that we are dealing with here? We have to look at that sampling function, xp. Remember, the sampling operation was what? X of t multiplied by xp of t to produce the sampled signal xs of t, right? So now I need to look at all of this from a frequency domain perspective. So I need to figure out what's the frequency domain of this guy, what's the frequency domain of this guy, what's the equivalent of doing this multiplication in time from the Fourier transform properties table, and then accordingly I can find how this sampled signal would look like. Okay, the resulting sampled signal, how it would look like in frequency domain. Okay, so started by assuming that my input signal has some shape in frequency, because we are talking about any general continuous time signal. The important thing, it has a certain limited bandwidth, okay? And let's look at xp. We know how xp looks like in time domain. It's a very specific function. This is our specific function, xp, the sampling function. Okay, and it's just the nice, with amplitude 1 train of delta function, okay, as a function of time. Okay, And remember that we wrote this as the summation from n equals minus infinity to infinity, delta of t minus n ts, right? This is how this train of deltas is written as a function of time, okay? Now, if you go to your Fourier transform table, you will find that a couple of interesting things, okay? Again, you can start thinking of this as like separate deltas. Each one of them is just a delta. And then for each delta, the corresponding frequency, for each shifted delta, the corresponding frequency domain representation is some exponential, just a pure imaginary exponential function. But also, and when you do the summation of those, there are some mathematical manipulations that allows you to represent them in a different way. Forget about that. You can from start think of this as when you have this train of delta, it's actually what? It's actually a periodic signal, right? It's the one period will have a delta and then zero, and then that repeats over and over again every ts, right? And now, I hope you watched the video that you will have a quiz on tomorrow. If you didn't, you will watch it probably today or tomorrow. Okay? It's gonna be, again, I will open it from midday until end, similar to what I did. I'm not gonna make it a very short time, so anyone can do it at their own time. Anyways, go back to this, okay? So, this is a periodic signal, and if you look at that video, you'll find that any periodic signal, when you perform Fourier transform on it, remember, periodic signal, we were able to represent them using the Fourier series representation. When we moved to the Fourier transform, we said it's a more generalized transform that allows you to deal with aperiodic, but also you can still deal with periodic signals. In the special case that you use Fourier transform on periodic signal, it produces actually delta functions with certain amplitudes. And the amplitudes of those delta functions in frequency domain with certain amplitudes, and the amplitudes of those delta functions are actually depending on what was your time domain signal. They can have values that corresponds to the Fourier series coefficients, but doesn't matter to us now. Anyways, based on that, keeping that in mind, if you just, this is a famous time domain signal that has its Fourier transform represented in the table of Fourier transform. So you don't even need to perform that operation of calculating the Fourier transform of this, relying on the fact that it is periodic and so on. You just need to look at the table, and you will find that the Fourier transform of this train of delta in time domain, interestingly speaking, is going to be also a train of delta in frequency domain. So versus omega, we still have a train of deltas, okay? And those train of deltas are spaced by value here, omega s, where omega s is equal to 2 pi over the sampling time ts. Okay? So if you want to represent, but they don't have a magnitude equal to 1, they all have equal magnitudes, and the magnitude of each one of them is 2 pi over ts, which can be written as omega s if you want, or just let's keep it this way, 2 pi over ts. So that's the magnitude of any one of them, okay? So they are spaced by distance 2 pi over ts, and their magnitude is equal to 2 pi over ts. But they exist at omega s2, omega s3, omega s4, omega s, and so on, which is 2 pi over ts, 4 pi over ts, 6 pi over ts, and so on, okay? So again, if you want to write this, it becomes in frequency domain, but I'd like to say 2 pi over ts multiplied by the summation of deltas. Now it's a delta of omega because it's a frequency domain function, and it's omega minus n 2 pi over ts, which is n omega s. Okay. Again, you can replace this. You can write this similarly as 2 pi over ts multiplied by the summation of delta of omega minus n omega s.
Okay.
Yes.
And the space between each of them is 2 pi over ts, and the height is 2 pi over ts.
Also 2 pi over ts. They have the same height, but again, yes, the space is 2 pi over ts, and the height of each one of them is 2 pi over ts. Yeah, so you can either write it this way, or 2 pi over Ts can be replaced by definition by what we call omega s. Okay? So this is again another train of delta in frequency domain. Okay, good. What else do I need to figure out? So now I figured out what's the frequency domain representation of this. I figured out what's the frequency domain representation of this. The next question is, what's the equivalent in frequency domain when I multiply two signals in time domain? If you go for, exactly, if you go for the table of properties of the Fourier transform, you will find that when I multiply two signals in time domain, so if I have the signal x1 of t multiplied by x2 of t, these are two signals, sorry, not convolution, multiplied. In time domain, those are two signals, I multiply them. If I go to frequency domain, the table tells you that it's going to be 1 over 2 pi, the x1 as a frequency domain function convolved with the x2 as a frequency domain function. Okay, so what's our x1 in this case? It's this guy. What's our x2 in this case? It's this delta function, this guy. Okay, those are the two signals that were multiplied together in time domain, and now to get the frequency domain result of that multiplication, I need the Fourier transform of the first, which I already wrote here as a general function, and the Fourier transform of the second, which is here, and then I need to combine those two Fourier transforms using convolution, not multiplication operation, and then the whole thing is scaled by 1 over 2 pi. Okay? So I can say that the result of this in frequency domain now, okay, so now I'm going to take this into frequency domain, and I'm going to write the same thing here. This is frequency domain, this is frequency domain, okay? So when I take this into frequency domain, it becomes the x of omega, this guy, right? Convolved with this guy, which is 2 pi over Ts, the summation from n equals minus infinity to infinity, delta of omega minus n omega s, right? And then don't forget that there is a 1 over 2 pi here from the properties table, okay? So that whole expression, when evaluated, when I can evaluate this convolution, is going to give me what x of s will look like in frequency domain, which is what I was seeking from the beginning, okay? Now let's look at this situation. When I have some signal convolved with, let's forget about the summation now. I have some signal convolved with a shifted delta. What do I get? The signal shifted at this is convolution, not integration, not multiplication. It's convolution, right?
By this x shifted to the location of the delta.
Yes. So okay. I will remind you of the property. The properties of the delta function. There were 3 of them related to how a delta function interacts with any signal. Okay. So if I have x of t just multiplied by a delta at t minus t naught, the output of this is going to be x at t naught. The output of this is going to be x at t naught, still multiplied by the delta of t minus t naught. So I just end up with a delta scaled by the value of x at t naught. And when I have the integration of x of t multiplied by delta of t minus t naught, and I integrate with respect to time from minus infinity to infinity, this is going to be just the value of x at t naught. So it's simply x at t naught. Okay, that's the second property. The third property was if I have x of t convolved with a convolution of x of t with delta t minus t naught, I get a time function, a continuous time function, but shifted by the location of the delta. So it's x of t minus t naught. That's what I get. Okay? So when I convolve any signal with a shifted delta, I end up with the signal itself shifted. Okay? Not just taking a single value of the signal, I'm actually keeping it as a time function signal, but that time function is shifted. Okay? That's the result of convolving a shifted delta with a signal. So that's what we have here. We have a shifted delta convolved with x of omega, right? And the rest are constants. And the summation can be outside. So I end up with what? So I can say here, if I just take this up, I can say that 1 over 2 pi x of omega convolved with 2 pi over ts summation from n equals minus infinity to infinity delta of omega minus n omega s is going to be equal to, let's just cancel these things, so I end up with 1 over ts, right? Just a scaling factor, and then the summation, and I can take the x of omega inside with the convolution operation also inside the summation, so from n equals minus infinity to infinity, x of omega convolved with delta of omega minus n omega s. And now this, from this property, is going to be equal to x at omega minus omega s, right? When you convolve x of omega with delta of omega minus omega s, or n omega s, you end up with x of omega minus n omega s, right? It's very interesting. I will show you why. So this is equal to 1 over ts, the summation of n from minus infinity to infinity, x omega minus n omega s. That's the final result, right? Forget about the scaling factor now, doesn't matter. Okay? Because we are seeking some conditions in ts, and we expect that this condition is going to have to do somehow with the bandwidth of the signal property. So the amplitudes doesn't matter, but you can keep it or you can forget about it, doesn't matter. Okay? Look at this. If you want to graph this expression, how it would look like in frequency domain. I want to graph this. Okay? So let's try to do this together. So we continue with what we reached so far is that our x s of omega, the sampled signal. Sorry?
Can you go back to the last line? I want the answer.
You want of the last slide was that the sampled signal in frequency domain, xs of omega, is equal to 1 over ts, the summation from n equals minus infinity to infinity, the original Fourier transform of the signal, the original Fourier transform of the continuous time signal x of omega, but not as is, shifted to locations n omega s. Why do I say locations? Because we have a summation here. So every time we change n, we have another replica of that spectrum at the location of omega s, right? So if I want to plot this, what do I have? If I want to plot this, remember that x of omega itself looked like this, right? Just some with bandwidth b, right? This is how it looked like when we did it, or we assumed it looks like this, right? With certain bandwidth. So now if I have, let's put n equals 0. So if I put n equals 0, I will get the same original one, right? X of omega only. So I will get something like this, right? Sorry. With b. And now let's put n equals 1. When n equals 1, I will get the same shape, but centered around omega s, right? Because it's shifted with an omega s value. So if its center value was 0, now the center value becomes omega s, right? So I will get the same shape like this, b, and the center point here is going to be omega s. And if I put n equals 2, and I get the same shape, right? With bandwidth b, and bandwidth here means the distance, this distance, okay? Doesn't mean that the end point is b, okay? And okay, let me just put this the right way so it doesn't confuse you. say that the bandwidth here is B. And this is shifted to 2 omega S, and still the bandwidth here is B, right? And so on, okay? Similarly, I will have replicas from the negative side. Okay. So assume that this is how it would look like, okay? And the word assume has a reason that I will mention in a few minutes, okay? So we have the main spectrum replicated at omega S, replicated at 2 omega S, 3 omega S, minus omega S, minus 2 omega S. So that's exactly the expression that we have up there. The x of omega shifted one time to omega S, shifted another time to 2 omega S, shifted a third time 3 omega S, and all of these are added together. So when you add them, you have replicas of the same spectrum of the original signal. Now, if this is the shape of the signal, the sampled signal, okay? This is how it looks in frequency domain, just the main spectrum repeated many times, okay? If I want to recover from this the original signal, what should I do? If this is the sampled signal, and I want to recover the original one, what should I do with this sampled signal? Let's agree on the calling that this is omega and this is our xs of omega, okay? So if I want to recover the original one, what should I do? I should find a way to remove those replicas and only keep this one, right? If I do this, I recover the original signal, right? So from what we see here, to recover the original signal, and I will still talk frequency domain now, x of omega, from xs of omega, I just need to keep the spectrum around 0, this guy, right? And eliminate all other replicas, right? So I need to somehow eliminate this, and somehow eliminate this, and somehow eliminate. That's to recover. So far, we have seen when I sample my signal, when I sample x of t, which is a frequency domain called x of omega, when I sample that by the delta functions, which means in time domain I pick values from it and throw the others, right? When I look at the frequency domain, what happens to the signal? Very interestingly, the frequency domain representation of the signal is repeated, right? That's what happens. That's what I see when I look at the frequency domain. That's the effect of sampling, right? So if I want to recover the original continuous, I simply, by looking at frequency domain, it's apparent. If I can get rid of those guys and only keep this, I have recovered my original x of omega, which means I've recovered my x of t, the continuous time signal, right? How can you do this? How can you reject everything and keep only a particular band using what you used in your project? Using, which is called filter. You use a filter around 0, a low pass filter, right? So simply, all you need to do is use a filter with a width equal to the bandwidth of the signal, so it doesn't cut anything, but it makes sure that it cuts all the other guys, right? So you use a low pass filter with, so to recover, this is equivalent to using a low pass filter with bandwidth equal to the signal bandwidth B, right? And that filter is going to reject all the other guys and keep only the middle one perfectly as it is. And then this means you got x of omega, and when you look at it from a time domain, you take off the glasses of the frequency and you put on the glasses of the time, you will see actually you recovered your continuous signal. That's very interesting, right? But from a physical point of view, it has a meaning. A low-pass filter does what when you put impulsive signals to it? It tries to interpolate between them because it doesn't drop very quickly. When you have a low-pass filter, like an RC circuit, for example, okay? When you put a value on it and then just make the value disappear because of the capacitor, it will not disappear immediately. it will try to drop slowly. And then you get the next value, so it's kind of going to interpolate between one sample and the next one, right? So that's basically physically the effect of a low-pass filter. Just I'm gonna draw an explanation for this. This is the operation of when you have a pulse put into the signal, right? Some pulse put into your circuit or your filter, and then another pulse. The filter cannot trace the pulse. It's going to actually try to kind of move smoothly from one pulse to the other because it's a low-pass filter. It just doesn't change abruptly. It will keep changing slowly. And this effectively is an interpolation process, which is going to recover a continuous signal from the original, from the sampled signal, okay? If you meet the condition, now let's look at the condition. So far we did not discuss the condition, right? Why did I say assume it looks like this? Because who said that when I move to omega s, right, that replica is not going to interfere with the one before it. I only assumed here that this is happening by drawing them, each one separated from the other, right? But it depends on the value of omega s. If the value of omega s was too small, so if omega s occurred here, then this replica would have actually interfered with the one before it. This means that there are two spectrums added together, because that interference means that the two signals are added. And the shape of the resulting spectrum is not going to be anymore the original shape. So if, let's start by that replica thing, x s of omega as a function of omega, and we have those nicely selected guys to be easy to graph, and still I cannot make them look similar to each other, but anyways, so this happens at omega s, this happens at 2 omega s, this happens at 0, this happens at minus omega s, and so on, right? If omega s was too small, this means what? This means Ts is too big, right? Okay, what will happen? This guy is going to get closer, and at some point the next replica is going to interfere with the current replica. So if the location of omega s becomes, for example, here, what I will end up with is a situation that looks like this. This is one replica of the spectrum, this is the second replica, this is the third replica, right? And if I actually put these replicas together and take into account that they are added together, so at the points where they intersect, you have to add the values from this function with the values from the next function, I will end up with some spectrum that looks like this. Right? I can no longer, by any filtering, in this case, recover the original shape of the signal around 0. So no matter what I do with this resulting signal, I will not be able to recover the original signal. So now the condition is that omega s has to be large enough to prevent any overlap between the replicas, right? Now, if we want to deduce that condition, how do we deduce it? We can deduce it, right? If this is omega s,
We decrease Ts.
yeah, if just by calculation from the graph, right? If this is omega s, and we know that this is b, and the spectrum is always symmetric, so this is also b, right? So what's the value here? If this is omega s, then this value is omega s minus b, right? And what's the value here? This is b, the bandwidth of the signal. Don't forget these are replicas, so they have the exact same bandwidth, right? So the centered around 0 will finish at b. The one centered around omega s will start b before omega s. So it starts at omega s minus b. Any issues with this? This spectrum is with width b from each side, and it is centered around omega s. So what's the start point? The start point, look at it. The one around omega s. If it's centered around omega s, and it has a width b this way and a width b that way, what's going to be the start point? Please. Look at this one. Okay? The center point here is called omega s. It's a value omega s, right? and the width of this is B, and the width of this is B. So what's going to be this point? If this is omega S, and the width here is B, what's the value here? Minus B, exactly. That's what's written there. Okay? So that point must be greater than this. Otherwise, what will happen? They will interfere, right? So the condition is going to be simply that omega S minus B, this point, has to be greater than this point, so greater than B. And this results in omega S has to be greater than 2B. So now we see that in order for your sampling not to cause that interference, which is going to prevent you from recovering the original signal correctly, you have to make sure that you sample with an omega S, and that omega S is just 2 pi over Ts, right? So you have to sample with an omega S that's greater than double the bandwidth of your original signal, right? And this is what is called the Nyquist sampling, and this whole expression is what's called the sampling theorem. So the sampling theorem says okay, it says that in order to be able to have a unique representation of a continuous time signal using its sampled version. Okay. The sampling frequency, omega S, is called the sampling frequency. Sampling. Again, this is frequency in radians. You might find other conditions that rather than saying omega S, it says Fs. The difference between Fs and omega S is just a 2 pi factor, right? Omega S is equal to 2 pi F S, okay? And if omega S is 2 pi over Ts, then Fs just the inverse of Ts, 1 over Ts. I will mention all of these, okay? So anyways, the sampling frequency, okay, omega S has to be strictly greater than 2B, where B is the bandwidth of the continuous time signal. And if you meet that condition, your sampling is perfect. It's proper. That's what I called proper before, in the sense that you can always recover your original continuous time signal from the sampled version. If you don't respect this condition, then once you do sampling, if you try to recover the original signal, you will never be able to recover it. You will recover some distorted version, which is not the correct one. You will lose some information, okay? But if you respect this, then moving from the discretized or the sampled version back to the continuous is going to be lossless, and you will recover your continuous signal the same way as it used to be. Similarly, the example of this in your project is when you took those audio files, they were already converted from continuous, whoever speaker talked to the microphone or recorded whatever the voice on the internet or whatever, they were taken with a certain number of samples, and you'll find that like probably most of them, they were, for the wave files, they are 48,000 samples per second. Okay? So there was a particular sampling frequency used there. And if you drop, you know that your signal, that's what you found, typically is between 6, maximum 10 kilohertz, right? That's the bandwidth. So the minimum sampling frequency is going to be something like double that, right? So it's going to be the minimum sampling is something like, if it's 10, then it's 20. And if it's 6 or 7, then the minimum sampling is like 12 kilohertz or 14 kilohertz. They use a little bit more because that allows the quality of the sound to be more resilient to noise. But if you go below the minimum, if you go below what this theory says, you will never be able to recover the actual voice on the speaker. You will just get some something that does not mean anything, okay? Get some noise, but you will not get the original voice when you try to produce it at the speaker, because at that point it has to be continuous again. Okay? Anyways, so that's basically what the sampling theorem says. It says that your sampling frequency omega s, and again, the relations just for you to know, omega s is equal to 2 pi over ts, the sampling time, and omega s is equal to 2 pi fs, the sampling frequency, but in hertz rather than being in radians. And the last relation is that based on those two relations, that fs is equal simply to 1 over ts. So if you deal with the sampling frequency just in hertz, here the units are hertz, then it's simply 1 over the sampling time. If you deal with sampling frequency in radians, it's 2 pi over the sampling time. I will write the units for you as well. So this is in radians, okay, and this is in hertz, okay. And of course, TS is in seconds, right? No need to mention that. That's just time, so time units, okay. That's the sampling theorem, okay. Now, based on what we did already, based on what we looked at, if you respect the sampling theorem, the one remaining thing that we need to discuss conceptually is how you do reconstruction, right? So we already addressed that when we were trying to find the condition, right? So simply the inverse operation, the reconstruction, okay, or the inverse of sampling. What does reconstruction in this sense means? It means that you have some sampled signal of of ts, of t, or x of n, whatever you like. It's just some discrete signal, right? Getting into your system, and then you perform the reconstruction operation, and what you get from the other side is your original continuous time signal x of t. That's the reconstruction operation. And we have found from what we discussed a couple of slides ago that this operation can be performed successfully if you have respected, so assuming the sampling theorem is satisfied, okay, then the reconstruction operation is simply what? What did we notice when we looked at frequency domain? We had those replicas and we wanted to recover the signal. The reconstruction was simply low pass filtering, right? Is simply low pass filter of x s of t, right, using a filter with bandwidth equal to b, where b is the bandwidth of our original signal x of t. Okay? So if you use a low pass filter with bandwidth b on your sampled signal, what you will get out of that filter is going to be simply your continuous time signal perfectly back again. Of course, all of this assuming that we live in an ideal life. When we live in a practical life, but we will not address this in this course, you cannot really get delta functions in the first place because they are very short functions with very high magnitude, so that's impossible to get practically. You work with pulses that are short as much as you can and with amplitudes as high as much as you can without saturating your electronics, and your electronics will have finite response time, so they will never create a pulse with a width equal to 0, right? So you will work with non-ideal sampling functions, and accordingly the sampled signal is going to have some non-idealities. Not only that, there is no such a thing like a really finite bandwidth signal. You will deal with signals that never goes to 0 in frequency domain, so you'll have some overlapping. All of this will add some distortion to your system, but still with very reasonable quality, very minimum error, you can still recover everything correctly with certain, what you call in engineering design, with certain margin of error or margin of safety, right? So you design, for example, instead of saying that my filter bandwidth is going to be B, is going to be slightly bigger than B, instead of saying that I sampled immediately at something equal to double the bandwidth, maybe I use like 3 times the bandwidth to give a little bit more space to deal with non-ideal filters and non-ideal pulses and so on. So you grow things a little big, you over-design a little bit beyond the theory so that you can recover your signal correctly, okay?
And the filtering, don't you apply to the frequency?
Sorry?
The filter, you apply to the frequency domain and then you have to do the inverse.
Again, when you do the inverse and stuff like that, it's just how you look at things. But what you do in frequency domain happens in time domain, the correct way. When I go to frequency domain and I filter a signal, it is actually from a time domain perspective producing the correct output, right? But it's only which one I look at, right? Again, it's as if this is your signal, right? And we said it has like two perspectives. This is time domain, this is frequency domain. But both of them are the two sides of your signal, which is this shape, right? Now it depends. Am I looking at this or am I looking at this, right? In all cases, if I do this to my chair, right? Whatever I see happening here, the corresponding part of it happens here. If I do this to my chair, I did this while looking from here, so I only see what happens here. But the corresponding effect is already happening in time domain, right? So simply, when I do that low-pass filtering, and I see that I cut the replicas, this is effectively that the sampled version becomes a continuous signal in time domain, okay? Did I convince you? Okay. Okay.
Doctor, can we take attendance now? We have a quiz.
Yes.
So,
Yeah, we can take attendance now. So far, we have looked at how to perform the sampling operation itself, and then what are the conditions for that sampling operation to be, or that sampled signal to represent uniquely the original continuous time signal without loss of information, and that comes under what's called the sampling theorem. And then, as part of that, we have already figured out how you can reconstruct the original signal, how can you recover the original continuous time signal, which is called the reconstruction operation, which is the inverse of the sampling operation. So you have a sampled signal, you put it to the reconstruction filter, and it comes out as a continuous time signal, right? So we figured out that in order to perform this by looking at frequency domain, we already found that if we go to those replicated spectrum version of the signal, which happens when it is sampled, if you remove those replicas and only maintain the middle one, which is effectively a low-pass filtering operation, you end up with your original continuous time signal recovered. Now, just for what do you call them, housekeeping or terminology issues, I'll mention some of the important terminologies here. So we have this, the sampling theorem, right? Says that your sampling frequency omega s has to be greater. Notice that it is greater strictly, so it cannot be equal. Has to be greater than double the bandwidth of your continuous time signal. This value, double the bandwidth, they call it Wn, which is called the Nyquist frequency. Just refer to a mathematician who had played a major part in discovering the sampling theorem. And that double bandwidth, we call it the Nyquist frequency. So another version of the sampling theorem can be written as omega s is greater than the Nyquist frequency. Okay? Don't forget that that Nyquist frequency is actually double the bandwidth of your sample signal. That's one important piece of information to keep. It's related more to the terminology and naming. It doesn't really change the theorem or anything. The other thing is the effect that happens when you don't respect the sampling theorem. So when you sample at a frequency less than the Nyquist and you cause this interference, this effect is called aliasing. This interference between the different replicas that prevents you from recovering the original signal is called the aliasing effect. Okay, so this is when you use omega s, which is not greater than 2b. So when you use omega s, which is smaller than 2b, in this case, this aliasing effect, and it prevents you from recovering the original signal. So when omega s is smaller than 2b. Yeah, the issue with equal is it's a critical situation, so we don't address it as part of the general theorem. I'll tell you why. The equal case works in some signals and it doesn't work in others. Particularly if your time domain signal, the continuous one, sorry, both of them are time domain. If your continuous time signal was periodic, then if you sample at exactly 2b, you will not be able to recover the original signal. There will be ambiguity. You won't know what was the shape of the original. You'll have multiple ways to represent the original continuous signal. If your continuous signal was aperiodic, then yes, you can work at exactly 2b. So that's why the theorem, to be more general, it just avoids the situation of 2b, neither in the aliasing nor in the condition itself. Okay? So that was a very good question. So that at least we mentioned that point, and we don't forget about it. Okay? So more or less, these are the important terminologies that you have to keep in mind. So when someone talks about aliasing, you understand that this is a situation where your sampling frequency did not satisfy the sampling theorem, and accordingly your signal is going to be distorted and you will never be able to recover the original continuous time signal. Okay? And the Nyquist frequency, you just understand that this is simply double the bandwidth of you. That's the critical frequency that you have to be above in order to sample correctly. And it's exactly equal to double the bandwidth of your continuous time signal. Okay. Now let's solve an example. Any questions before we go to the example? All good? Okay. I think the example will clarify things in terms of a little bit more understanding, and also how you address problems, what kind of problems you can get on this topic. Okay. So problem here gives you x of t, some time domain signal. I don't know why I wrote it this way. X of t, some time domain signal, and the problem itself tells you that x of omega looks like this. Okay, so this is your x of omega. Okay, and it has a bandwidth here. The bandwidth of your signal is equal to 350 kilohertz. So in many cases, we give you, especially in sampling problems, in most of the cases, we give you the signal in frequency domain, so that you know the bandwidth of that signal. Okay. But sometimes you might get a time domain and it's your job to estimate the bandwidth by converting it to frequency, okay? Most of the time it's similar to this. So this is your x of omega. You have a signal, sometimes by a graph, sometimes you are told that you have a signal x of t which has a bandwidth equal to 50 hertz or 50 kilohertz or 10 kilohertz or whatever, okay? So given by a graph or told in a statement, it's the same. You just know the bandwidth of the signal. And the question says, find, okay, the Nyquist frequency, okay, or find the minimum sampling frequency, okay, which means the same as finding the Nyquist, okay, for x of t. So what's the sampling frequency that you should use to properly sample x of t? Okay. What's going to be the answer here?
Less than 2.
Greater than. Yeah.
Oh, okay.
Greater than, right? So the sampling frequency omega s, if you write it as omega, so be careful because it's given here to you, the bandwidth is given in hertz, right? So you have to convert it. Or you can make things easier for yourself and you just say fs, the sampling frequency, is equal to double the band, not equal to, sorry. Fs has to be greater than double the bandwidth B.
We didn't flip it.
Why do we flip it?
Wn is greater than 2B, right?
Yes, Wn. No. Nyquist frequency is exactly 2B. Sampling frequency has to be greater than the Nyquist, right? Nyquist n, Fn is equal to 2B exactly. Fs has to be greater than 2B or greater than Fn, right? Okay. So the sampling frequency has to be greater than double the bandwidth of the signal, which means that Fs has to be greater than 2 times 350K, which means that Fs has to be greater than 700 kilohertz, right? Or you can tell me that the Nyquist frequency is equal to 2B. So now we are looking for the Nyquist. The sampling, you give it a range. It has to be greater than 2B. The Nyquist is defined as 2B, right? So Fn, the Nyquist frequency, is just double the bandwidth, which is equal to, so Fn is equal to 700 kilohertz, okay? If for some reason you decide to solve by Ws, then Ws is greater than 2B. But in that case, you are talking about 2B in radians. Don't forget that. The 2B that you have here is in hertz, okay? So don't forget to convert. So this says that your Ws has to be greater than 2 pi times 2B in hertz. This is 2B in hertz, okay? So it's Ws is greater than 2 pi times 700K. Okay? So if you use omega or W, the radian frequency, make sure either that the graph there is showing things in radians or you convert to radians. Don't forget that. Okay? Or the other option is just, since the values on the graph or in the text was given in hertz, just use Fs and Fn instead of Ws and Wn, the Nyquist frequency, okay? This is a simple question. Another question that you might be asked, which requires you a little bit to understand where the sampling theorem came from and all these operations that we performed in time domain and frequency domain to discover the sampling theorem and so on, is gonna come in the next slide. But before going there, any questions here? All clear? Okay. So here is another type of question. Okay. Here is your signal. Let's say it's just a triangular. This is your x of t, x of omega. And you were told that it has a bandwidth equal to 1 kilohertz. And this is your frequency. Maybe this, in this case, it becomes x of f, okay? So this is your frequency domain representation of the signal, and it has a bandwidth equal to 1 kilohertz. And then it says, for the signal, okay, x of t, which has x of f as shown, find the minimum sampling frequency, and it specifies Fs, so it tells you that you need to calculate things in hertz, okay? Taking into account that allows unique reconstruction, right? That's just the definition of the minimum sampling, okay? Taking into account that you only have access to reconstruction filters with bandwidth, this is the bandwidth of the filter, equal to 5 kilohertz. So now the restriction might be from the signal, might be from the reconstruction filter, right? So how do we look at this? Just draw the figure that we did when we were trying to derive the sampling theorem, right? So in order to solve this problem, you will just try to see, okay, here is what happens when I sample the signal, right? I end up with replicas happening at Fs and 2Fs and so on, right? And the bandwidth of this signal, is equal to 1 kilohertz. So this point is Fs minus 1 kilo, right? And this point is Fs plus 1 kilo. So معايا? Are you all with me? What I'm saying is correct? Okay, تمام. Okay. Same here, but this is centered around 0, so this point is 1 kilo, and we don't care about the negative. We just have it for mathematical representation, and we have to keep it, but we don't go there and start looking at the negative side. Doesn't matter now, okay? But the problem tells me that when I'm going to reconstruct, when I want to do reconstruction, unfortunately my reconstruction filter cannot have a bandwidth of 1 kilo. The only reconstruction filter that I have access to has a bandwidth equal to 5 kilohertz. So on the same figure, draw your reconstruction and just in terms of scale, try to make sense, okay? So this is your 5 kilo, for example. Okay? So this is the end of the filter here is gonna be 5K. Right? That's, of course, it exists on the negative side, but we will only calculate from the positive side. Okay? So this is your reconstruction. Now, in order for this reconstruction to be able to recover the original signal without taking anything from the replicas, the next replica has to exist outside this range, right? Because if it was closer, well, I cannot really make this smaller because the only available is the 5K. So now I have to make sure that I sample and push the next replica to be outside the range of the low pass filter. The restriction now does not come from the signal spectrum itself. It comes actually from my reconstruction filter, right? Otherwise, I have to use this, and if this was a little bit closer, even though it's not going to overlap with this, but unfortunately what I will get is going to be this with a piece of the next one. So that's again not the original signal. That's something else. Okay? So I have to make sure that this point is greater than this. This point is Fs minus 1 kilohertz, right? And this point is 5 kilo. So now it says, the equation says Fs minus 1 kilo has to be greater than 5 kilo, right? So the final result is my sampling frequency has to be greater than 6 kilohertz. That's it. That's the minimum sampling frequency that I can work with under this practical requirement that my reconstruction filter, I don't have a nice one. I only have this available for me. So now I have to sample a little bit higher than the Nyquist, much higher than the Nyquist actually, just to make sure I can recover the signal again using the hardware that I have, the reconstruction filter that I have. Okay? So you can think of other variations, but these are at least good ways to see that what's a direct question in terms of sampling, and what's a question that requires you to a little bit understand in depth where the sampling theorem came from and calculation of the sampling frequency for that particular value. Why? Mainly the idea is to be able to reconstruct. Now if the restriction of the reconstruction comes from the signal itself, I don't want the replicas to overlap, then that's the sampling theorem. If it comes from other aspects, I have to look at the spectrum and see how the other aspects fits into the design of my system. Okay? Any questions about that? Okay. Last thing, and that's probably an easy piece for computer engineering students, but also for electrical, is in many cases when we deal with digital systems, okay, for example, the computer, right? It's not enough to have samples of the discrete signal. Yes, this eliminates the need for a continuum of values, which means too many values. But there's another aspect that I have to keep in mind, precision, right? So a computer can perform representation of numbers up to a certain precision. Now precision comes into what? What are the values of the amplitudes of those different samples? If I keep the values of the amplitudes continuous, I need an infinite number of bits to represent every single value, right? And that I cannot afford it in any computational system, right? If I allow the amplitude to be anything from, let's say, 1 to 5, but it can take any value with infinite precision, right? Then this means, with infinitesimally small precision, this means that simply I need a very large number of bits to represent any value of the samples, right?
You mean the decimal points?
Yeah, if I allow the decimal point to extend all the way to whatever,
Infinite possible values.
yes, so this means I need an infinite number of bits, right? I cannot do this. So I end up doing what? I end up typically saying that each value, for example, if you use the float representation, each value is 4 bytes. If you use the long representation, it's 2, I don't know, the float is 4, 8, there are some, right? Anyways, each value is represented by a certain number of bits, okay? So you have to keep that in mind, that in digital systems, values of sample amplitudes, okay, have to be represented by a finite number of bits. And these are gonna be certain number of bits, call it B, per sample, right? Per sample, I have B bits, right? For each sample, to represent its value, I'm gonna use a number of bits B. Now, when I sample my signal with a certain frequency, Fs, so sampling at frequency, whatever your sampling frequency is, call it Fs, right? And for each, this is Fs samples per second, right? Or hertz, it's the same thing, okay? For each sample, I have B bits per sample. The resulting bits per second is going to be what? I have Fs samples per second. Each sample of those is represented by B bits. For each sample, I have B bits. So what's gonna be the resulting bits per second for this whole system? Let's put it in numbers. If I have 10 samples every second, that's 10 samples per second. Tamam? And each sample is represented by 2 bits. How many bits per second I have? 20. It's 2 times 10. So it's B times Fs, right? So simply this is gonna be Fs times B. The sampling rate, the number of samples per second, multiplied by the number of bits per sample. Okay? And we call this the rate in bits per second. Yes?
What is after Fs?
Huh?
Yeah.
Samples per second. Okay?
What's R? R U.
It's gonna be the resulting rate in terms of bits per second. We call that the rate or the bit rate needed for this particular operation or this particular system or this particular calculation or whatever. Okay? Done with the sampling. Any questions? Done with whole, whatever we needed to discuss in this chapter is finished completely now. Any questions?
Doctor, this doesn't have restrictions?
Sorry?
This doesn't have restrictions, for example, the precision, if it's not...
I mean, you can do that, but I'm not gonna go because that's more towards the computer science and computer engineering. It's computing rather than signals and systems, okay? So yes, again, where do I find the B, the number of bits needed to represent? Of course, if you are a computer engineer and you want to calculate that, or a computer scientist and you want to calculate this, then you will go to, and you will ask me what's the number of precisions, how many digits after the float, and how many digits before the decimal point, and accordingly I can calculate for you the required number of bits. But we don't go there. Typically, in these questions, or if I ask about the digital rate or the bit rate, I will give you the number of bits that I use to represent the sample, and then you just need probably to calculate Fs from the sampling theorem or from something similar to the problem that we solved, and then to get me the total bit rate, you just need to multiply that calculated Fs with the given bit rate, bits per sample, okay?